In May 2017, scientists offshore Sicily ran a routine sensor check beneath Mount Etna. Suddenly, their equipment recorded a silent, invisible jolt. The volcano's entire eastern flank had slipped more than 4 centimeters in just 8 days. This is not supposed to happen. If Europe's most active volcano is truly sliding into the sea, what force is pushing it, and how much time do Sicilian communities really have? The answer changes everything. On the research vessel Poseidon, the routine of a quiet evening shattered when the acoustic console erupted with numbers that didn't make sense. Dr. Marilia Urlaub and her deck team stared at the raw readouts from the seafloor array, expecting the usual fractions of a millimeter and small daily changes. Instead, the baseline distances between transponders had jumped by 4 centimeters, not over months or years, but in just 8 days. The data streamed in every 90 minutes, each new measurement confirming the previous one. Urlaub scrolled through the time series, searching for a glitch. The instruments anchored 1.2 kilometers beneath the waves had been steady for nearly a year. Now, every line across the submarine fault showed the same abrupt eastward shift. Crew members gathered at the workstation, trading nervous jokes that something must have gone wrong with the equipment. Someone suggested a clock error, maybe a battery fault, perhaps an acoustic signal lost in deep-water static. But the pressure and temperature logs looked clean. The system's internal checks had flagged no malfunction. Urlaub called for a manual calibration, running the numbers again. The answer didn't change. The entire monitored section of Etna's underwater slope had moved as a single block, sliding seaward in silence. The logbook entry for that night is terse, but the word shock appears more than once. No earthquake, no eruption, no surface warning, just the sudden invisible motion of a mountain's flank, caught in the act by a string of digital pings. For the Poseidon team, the implications landed hard. The event was not a minor tremor or a slow creep. It was a clear, measurable displacement, 4 centimeters across multiple baselines, with no obvious trigger. The raw numbers spoke for themselves, and for a moment, the familiar world of volcanic risk felt newly unstable. Calibration began immediately. Technicians double-checked the acoustic transponder's internal clocks, running through every step in the maintenance manual. Each device pinged its neighbors, logging two-way travel times down to microseconds. The pressure and temperature sensors, built to flag even the smallest drift, reported stable readings. No sign of battery sag, no evidence of signal loss in the water column. The team cross-referenced baseline measurements against the last year's data, looking for any hint of instrument drift or environmental interference. Every check confirmed the same outcome: 4 centimeters of sudden horizontal displacement spread across all fault-crossing baselines. Data integrity checks continued. The crew moved to manual recalculation. They pulled raw acoustic waveforms, reran the sound speed corrections using in situ temperature and pressure logs, and compared the results to backup calibration routines. Each adjustment nudged the numbers by less than half a millimeter, well within the system's noise threshold. No processing artifact could account for the shift. The data held firm. With the integrity of the measurements established, attention turned to the numbers themselves. A 4-centimeter slip, measured across a fault more than a kilometer below the surface, represents a massive release of tectonic energy. The team calculated the seismic moment as 1.2 times 10 to the 16th Newton meters. That is the kind of energy usually reserved for moderate earthquakes, yet the seafloor had moved in silence, with no seismic signature, no surface tremor, no warning. Poseidon's logbook for that night records the crew's unease. Years of routine monitoring had never produced anything like this. The instruments had passed every test, the math was sound, and still the numbers defied expectation. For the scientists, the only rational conclusion was that the volcano's flank had truly shifted, and the evidence was now undeniable. On the slopes of Mount Etna, a web of ground-based sensors keeps constant watch. Each device records the smallest shifts, movements often measured in millimeters. Boris Benke, a volcanologist with INGV Catania, stands over a cluster of GNSS receivers and seismic tilt meters, their antennas fixed to bare rock and concrete. These instruments are not just technical hardware, they serve as the volcano's pulse monitors, translating the mountain's slow eastward drift into precise numbers. The GNSS network, spread across Etna's unstable southeastern flank, sends real-time position data to researchers. Over months, these stations reveal a pattern. Points on the lower slopes are marching steadily toward the Ionian Sea. The movement is not random. Every year, the eastern flank slides several centimeters, with the fastest rates, up to 14 millimeters per year, recorded near the summit and even higher values at the volcano's submarine base. This is not just a local quirk, it is a coherent directional drift, strongest along the same fault system traced offshore by Poseidon's seafloor array. Plots from the GNSS stations show a clear trend. After the 8-day slip detected at sea, onshore data echoed the same eastward jump. The ground-based sensors registered a synchronized displacement, no tremor, no eruption, just a silent step forward. Seismic tilt meters buried at key points along the fault picked up subtle changes in ground angle, confirming that the land surface itself had shifted in line with the underwater readings. Banke points to the overlapping traces on his monitor. The GNSS vectors plotted month by month align almost perfectly with the submarine measurements. The land and sea are moving together as a single block. For years, scientists debated whether the main driver was deep magma pressure or gravity acting on weak marine sediments. The data now leave little doubt. Etna's sliding is not limited to the deep sea floor. It is written into the rock and soil right up to the summit, visible to anyone reading the charts. The mountain's slow journey toward the sea is not just theory, it is happening in real time, confirmed by every sensor on the ground. From hundreds of kilometers above Sicily, the Sentinel-1 satellites sweep over Mount Etna every 6 days, capturing the volcano's restless motion with radar beams. Each pass adds a new layer to the archive, a digital snapshot of the ground's position measured down to the millimeter. When scientists process these images with interferometric techniques, the result is a map streaked with colored fringes, each band representing a tiny shift in elevation or position. Over Etna's eastern flank, the pattern is not random. The lines bunch together in a broad, sloping gradient, tracing the invisible journey of rock and soil as they inch toward the Ionian Sea. Stacking dozens of Sentinel-1 passes, researchers build a time-lapse of deformation. The most intense colors cluster near the coastline, then spill offshore, outlining the volcano's sliding toe. Quantitative overlays reveal the numbers behind the hues. Annual displacement rates climb from a few millimeters near the summit to several centimeters at the submerged base. The sharpest gradient, where the color bands tighten and twist, runs along the submarine fault, matching the very section where Poseidon's transponders recorded their abrupt 4-centimeter jump. This satellite perspective offers more than a static picture. By comparing data before and after the 8-day slip event, analysts see a sudden, coherent shift in the line of sight maps, confirming that the displacement was not a local glitch or artifact. The entire offshore slope, from the lower flanks to the deep sea floor, moved as one. Sentinel-1's radar cannot feel earthquakes or hear acoustic pings, but it registers the aftermath with cold precision, a silent eastward lurch written in pixels and phase shifts. When these satellite results are layered over ground and seafloor measurements, the agreement is striking. The direction, magnitude, and timing of the movement all align. The strongest deformation appears at the submarine toe, exactly where the fault system channels the strain. For the scientific teams involved, this orbital confirmation leaves little room for doubt. The mountain's slow slide is not just a theory or a quirk of one instrument. It is a fact, mapped from space, and the evidence is now visible on a continental scale. Deep beneath Etna's eastern slope, the roots of the volcano rest on a layer that behaves more like a lubricant than a solid foundation. This basal zone is a mix of soft, clay-rich sediments, remnants of ancient seafloor saturated with water and volcanic gases. Laboratory tests on these clays revealed just how little resistance they offer. Friction coefficients, the measure of how much two surfaces grip each other, fall between 0.1 and 0.3. For context, dry granite can reach 0.7 or higher. On Etna's low-angle fault, even a gentle push can set the entire flank in motion. The secret to this weakness lies in the fluids. Pore spaces in the clay are filled with water, some driven upward by deep magmatic heat, some trickling down from rainfall. When these fluids become overpressured, meaning their internal pressure approaches that of the overlying rock, they push apart the clay grains, reducing friction even further. In some laboratory simulations, friction drops so low that the fault slides almost as easily as ice on wet glass. Geophysical surveys and seismic imaging confirm these findings. Magnetotelluric data show zones of low electrical resistance, a fingerprint of water-saturated clays. Pressure sensors installed at depth detect pulses of elevated pore pressure, especially after heavy rains or volcanic degassing episodes. Every time the fluid pressure spikes, the fault's resistance to sliding drops, making sudden movements possible without the need for an earthquake or an eruption. This slippery foundation explains why Etna's flank can move as a single, massive block. The volcano's bulk is perched atop a mechanical weak spot, one that is both naturally fragile and easily tipped into motion by subtle changes in fluid pathways or stress. For decades, textbook models treated Mount Etna's slow deformation as a side effect of magma pushing upward from deep within the earth. The volcano's bulk, anchored on the Sicilian mainland, was expected to resist any large-scale movement. But new measurements have forced a rethink. The evidence now points to gravity as the main driver, a mass of rock and ash perched on a weak, slippery foundation, slowly spreading out under its own immense weight. This is not how continental volcanoes were supposed to behave. The classic hazard maps, drawn with Etna's eruptions in mind, never accounted for the possibility of the whole eastern flank inching seaward like a glacier. The Valle del Bove, a vast scar on Etna's eastern side, offers a stark reminder that catastrophic collapse has happened before. Geological surveys trace its origins to a prehistoric event, thousands of years ago, when a massive portion of the volcano's flank gave way, leaving behind a depression several kilometers wide. That ancient collapse, long thought to be a freak result of violent eruption, now looks more like the natural endgame of slow, gravity-driven sliding. The same weak marine clays that underlie the present-day flank were likely at work then, lubricating the downward motion until the slope finally failed. Recent data reveal that the fastest movement is not at the summit, where magma pressure is strongest, but at the submarine toe, far below where the volcano's base meets the sea. This pattern flips the old model on its head. Instead of eruptive activity controlling the pace, it is the relentless pull of gravity, acting on unstable layers deep beneath the surface, that sets the rhythm. The realization unsettles even seasoned researchers. If a volcano as massive as Etna can slide, seemingly on its own, what else have hazard models overlooked? The warning signs are not just theoretical. They are etched into the landscape and written in the scars left by past collapses. In hazard simulations run by Italy's national research agencies, the numbers are unambiguous. If a large section of Etna's eastern flank were to break away and plunge into the Ionian Sea, the resulting tsunami could reach Catania's port in as little as 5 minutes. Modeled wave heights peak at 6 meters, enough to overtop seawalls and flood entire neighborhoods. The water would surge inland for more than a kilometer in some low-lying districts, with the first wave followed by a series of powerful surges. Towns along the coast, Asiriale, Reposto, Aci Trezza, face similar threats, with run-up depths between 3 and 6 meters depending on the local shoreline. The mechanics are brutally simple. As the submarine slope gives way, millions of tons of rock and sediment accelerate downslope, displacing seawater and sending a pulse of energy racing outward. The tsunami radiates across the Ionian Basin, but the nearest coastlines have almost no time to react. For Catania, the difference between a routine day and disaster could be measured in minutes. Civil protection models show that even with automated alarms, evacuation would be a race against the clock. These scenarios are not distant hypotheticals. The same fault system that delivered the 4-centimeter slip now sits under constant watch, its strain building in silence. The hazard maps, drawn from peer-reviewed simulations, leave little doubt. The physical threat is real, the warning time short, and the scale of possible inundation sobering. In the event of a sudden collapse, the window for action would be measured not in hours, but in heartbeats. At the port of Raposto, a fisherman leans on the rail and describes how, over the years, the sea has changed beneath his boat. He recalls anchoring in the same spot each spring, only to find new cracks in the quay or a sudden drop in the harbor bed after Etna's more restless weeks. He says that sometimes the seafloor just disappears in places they used to trust, as he glances toward the horizon. Along the waterfront, the head of the Port Authority points to repairs made after the last heavy rains, when sections of the pier slumped by several centimeters. For him, the numbers from satellite maps and underwater sensors are more than scientific abstractions. They translate into overtime for dock crews and rising insurance costs. A civil protection officer from Protezione Civile stands by a stack of emergency plans and outlines the reality of evacuation routes that thread through crowded coastal towns. He says they have minutes, not hours, if the slope goes. Their drills are regular, but the warning time is brutally short. Nearby, a resident of Asiriale recounts sleepless nights during the summer tremors, remembering the confusion during the 2002 eruption and the scramble for higher ground. She wants more information, not less, and asks why hazard maps are not posted in every school and shop. These voices echo a wider call for action. Scientists are pushing for a new generation of monitoring. Fiber optic cables for distributed acoustic sensing (DAS) are being piloted offshore, promising real-time detection of subtle ground motion. Proposals for marine drilling to sample the submarine clays remain on hold, waiting for technical approval and fresh funding. On land, INGV's plan to densify the GNSS network aims to catch every millimeter of movement. Yet every advance comes with a price tag, and researchers warn that maintaining and expanding these systems demands steady support. The urgency is clear in the data, and in the daily lives of those who live within sight of Etna's shifting slopes. Right now, Mount Etna's slow descent is not just a geological curiosity. It is a real-time warning for Sicily's coast. With satellite data confirming centimeters of movement each year, the potential for landslides and tsunamis grows. Nature's timetable remains unknown. The ground beneath our feet is shifting, even when we least expect it. Share your thoughts below. How should we prepare for what can't be predicted?